Minasan, konnichiwa, Samurai Engineer desu. Today, we will look upon the good building design and construction techniques, methods in the Philippines. So this part of discussion is necessary as an advocacy to help our millions and millions of residence owners to have a good quality homes as their final residence. Okay? Because, as we all know, in the Philippines, residential systems, residential buildings are the most or the majority application in building design. However, only the high-end, only the well-to-do families could afford to hire, to consult an engineer in order to have an engineered design of their homes. And I think it is not a study, but on my observation, I would confidently suggest that there are about 70% of our family residential homes that are not engineered. They are not designed. They are just made up by what? Experienced carpenters. Of course, they are not really bad. In fact, they are very experienced in that field, but it is not really thought about, designed in a proper way, and if the residence is even good enough, they are oftentimes over design. So we should take a look into this document and present a very current topic about Philippine building design. Okay? So let us proceed. Usually, these are the majority of our residential units, which are mainly produced by carpenters and foremen and laborers. Okay? They are not thought about, planned about. They are not even issued permit sometimes. Much of the time, there's no permit. There's no building permit. There is no construction permit. There is no other permit. Okay? Just because they are residential, they are the only ones who will suffer if this building collapse. So in that sense, if the building quality is not good, it is their own pain. It is their own loss. Okay, so that's why the enforcement, it is supposed to be enforced by the government system to be able to enforce the engineering law of different discipline. We have civil engineering law, we have mechanical engineering law, we have electrical engineering law. Those three are the main laws that governs this building. We also have plumbing law. Okay? And since they are often left in the hands of carpenters and tradesmen, so it is more on copy, as a copy-paste basis of type of design. If something works, the carpenter will use that idea to another place, to another place, to another home, to another building, to another area. Okay? So if some process, some method, or some steps are not good, they would what? They would modify it. So as if it is trial and error. But since they are over and overly designed, they are actually strong. They are actually strong, but somewhat costly sometimes. Okay? And oftentimes, they are using um, processes which are not really up to date. Okay? So that's why engineering system is being more and more applied in this area due to what increasing demand for up-to-date materials, technology, and requirements. Okay, so let us take a look. This document is actually supported by United Nations Special Unit for South Cooperation and International Strategy for Disaster Reduction. So, disaster reduction. So, we would like to advocate safe haven, safe place, safe homes for those people, for those lower class people. Okay? In terms of money, in terms of capital. No? So they are low on budget in terms of building or constructing their household. Okay? So let us follow. I am personally would like to follow the advocacy of these agencies and institutions to create a momentum that would lead to what? Helping hand from technical people, engineers with experience, and provide engineering help to those residential potential owners, potential owners that would like to get required permit from the government agency, like what? Building permit, construction permit, and utilization permit, no? Sanitary permit. So there are several permits that should be processed before construction could even take place. So this is from funding of the German Technical Cooperations and United Nations Development Program with the regional center in Bangkok, Thailand, and International Strategy for Disaster Reduction with their office at Geneva, Switzerland. So their purpose is to provide simple information to house owners, to house designers and builders, and building monitors to teach principles of good design and good construction in natural hazard-prone areas. One of which is actually Philippines, because we are in the earthquake-prone belt. So we are with Taiwan, with Indonesia, with Malaysia, with Japan, as the most earthquake-prone areas. Okay? So also we have natural hazards present in our Philippine environment. So thoroughly studied, they will also guide on whether to repair or rebuild damaged houses. How about those houses which experience some degree of intensity of earthquake? So Are we still going to utilize the building, or are we going to rebuild or repair? The descriptions are followed by code of minimum standards. Code, meaning we have still, although we are advocating minimum criteria here, we are still ensuring quality and sustainable building that still follow minimum standard set by the code. Okay? Since many concepts are not easy to describe, this document contains pictures of good practice and common bad practice to facilitate understanding, because what is the level of education, what is the level of understanding, what is the level of knowledge of those people that we are targeting to utilize this document. So that's why it is more on pictures. Okay? The photographs had been taken of construction practices in the Philippines. The Philippines are generally hazard prone to the whole range of natural hazards like what I've said: earthquake, landslide, and flooding due to storms and sudden downpours of rains. And what else? Volcanic eruption. The principle of these are designed to minimize vulnerability to natural hazards. So another concept is vulnerability, which is not an issue of any building code. However, it is an issue of humanity. Okay? To natural hazards, so that houses will be safeguarded. In an area that is prone to earthquakes and other significant natural hazards, not only principles of design are important, but also principles of construction. How to actually do it in real life, that is construction. Since the best designed houses, which has been well covered and painted, may hide serious structural defects in their actual construction. So the planning may be good, but the real construction may differ. These defects may lead to serious injury and death and loss of property when the forces of nature strike the house. Another important element in sustainable housing is spatial planning, building houses in places that are less vulnerable. So we may start with selection of areas, selection of location, locating it where it is safer compared to other nearby areas. Design must incorporate resistance to locally experienced hazards. So there must be some local information, local database, local experience by the technical people who would help these homeowners or individuals to construct their own homes. Let us develop a culture of safety in our buildings, not just doing the minimum and the cheapest, but building houses that will safeguard families and assets. So this is a word from Robin D. Willison, so who actually wrote this handbook. Hey. A forward from the United Nations Development Program with their director, Yiping Zhu. Okay. Also states that the focus on the experience of the Philippines in the course of rebuilding and recovering from the devastation caused by severe flooding and landslide in the past 3 years. So we are always having this periodic, year after year of flooding due to typhoons and substantial amount of rains. And how could we cope up? Okay. Is there any hope of coping up with this yearly phenomenon? As recent events have continued to confirm, disasters upset and negate hard-won development gains. So, it's positive development coupled with negative hazard happened due to what? Flooding, damaging millions or even billions of properties in a single typhoon or single volcanic eruptions. Disasters are increasing, and as awareness grows, these risks have become a major cause for concern worldwide. The fact that disasters are often the result of multiple interrelated causes, that means that societies have difficulties in addressing this global issue. Okay, as a result, disasters can have enormous, far-reaching consequences. We always experience this, in fact, that could change our lives, which are located mostly in developing countries like us. Indonesia, Vietnam, Laos, Cambodia. Yeah. Huh? So we are similarly situated with respect to that. And this publication, this document, is a practical guide to design and construction of houses during the reconstruction phase in the aftermath of a disaster. How can we cope up with the repair and reconstruction? So good design knowledge. Okay. Special Unit for South-South Cooperation supports the sharing of knowledge, expertise, and lessons learned in the past. So these are the background of why we have this advocacy supported by different agencies, and I personally would like to. Okay, so specifically, they have international strategy for disaster reduction. So they already have disaster, how to mitigate or lessen the impact of the disaster to the common tao. So also very important, because Philippines is regularly exposed to climate-related hazard. So let us go further. So one of the proponent also something to say about this importance of analyzing the hazard carefully. At least some knowledge that we gained in the past, we have to do it in our current situation. Shelters, basic human need. House protects us from climate and animals, and also a social cultural role as a center of family life. And that's a manifestation of self-identity. So it is almost a sacred necessity to demand some a form of housing unit. Even from ourselves, as a private person, we are not demanding it from the government, but the government has the responsibility to help us, at least in information, to give us the proper guidance on what to know. However, we have this advocacy, which create this book. So, we have mainly design principles, and the other part is construction and materials principles. So let us go to the first part, design principles. What are the concepts that we are going to use to meet the cultural, social, physical requirements of residents, to provide safe dwelling, to shelter them from hazards that may impact from their environment? The house must be properly designed. And because of this, the following aspects of a house or a structure must be considered in the design. Okay. Firstly, a house must be based on a strong foundation, and therefore this must be given primary attention. Problems with foundations not properly designed lead to unequal settlement. So this is a concept that we learned in geotechnical engineering. We know how to even compute this. We know how to even estimate this, and therefore we are what? giving this to the local experts. No? Cracking of walls and floors and structural weakness are being examples of the result with uneven settlement. So one of the simple ideas is to have a house that have a coherent and simple structure so that it could resist outside forces. Not a complex one, simple, like if you put up a single stone, because it is so simple, it is a very hard to damage, no? Hard to crack because of its simple structure. So as simple as possible will give us better and better resistance forces. Okay? How a structure is like the skeleton of the body. If it is strong, it protects the whole house. So since we are going to use the house as a shelter, we have a space, an area that we have to occupy later on, and that area should be protected by the skeletal system. We need skeleton because we cannot provide big amount of money to give you the stone wall like of heavy but strong structure, but also very expensive. However, we can only create a skeletal system that is so strong that could withstand enough degree of external forces and will be the one would connect the other parts or the other elements of the house to be holistically resistive to the outside environment. Okay? A wall should be supported by columns and need to be connected to them. Roof trusses must be flexible but strong enough to enhance safety. Walls and roof need bracing to resist lateral movement. So those are the things. Those are actually three things. No? Walls, roof trusses, walls. Okay? So we already described. What do we need to do with the walls? It should be supported by columns. Okay? What do we need to do with the roof? Trusses should support the roof. And the trusses must be flexible and strong enough. Okay? And walls and roof need bracing to resist lateral movement. So, in addition to walls and roof, their main structural elements should need bracing. Okay? So, we'll go to that. Again, another second one, main the third one is drainage plans are essential to good house design. Drainage, this is sanitary to protect us from biological hazard that could lead us to sickness and illness. Okay? So, drainage plans, essential. The design should carefully consider whether the house needs to be elevated to safeguard it from its contents from flooding. Because floods carries bacteria. Bacteria would expose us to dangers. Okay? So let us go further. So we already gave you 3 design principles and look at our details, no? Detailed topics. Foundation. So starting with foundation. So if we can get back to that, that is the first one. Aspect, foundation. Then second one is house structure. Then the third one is drainage. Okay? So we are now going into deeper details under the foundation. A safe house must have a strong foundation. That is the concept. The ground under the building has to bear the weight of the house. It has to have the soil prepared so that the foundation must be made stronger. So let us prepare the soil, stamping on the having preparation for the footings. If the house has more than one floor, the foundation must also be made stronger. So as the floor rises, foundation becomes bigger or deeper. Okay? Why? Because as we have said, the house is the load of the soil. So soil will support the weight of the whole house. So we should be able to prepare the soil for this load. Okay? Foundations are best when continuous under the house. If they are continuous, because there are foundations that are isolated foundation, but they are best when continuous under the house. So they are what? There are several types of foundation systems, and one of which, according to our practice and experience, it is best when continuous type of foundations are used. Is the building built on sand, rock, or clay? So those are the things that we need to see, to observe, look upon during our visual survey of the area. Sandy soil, rocky soil, or clay. What is the best type of soil out there? And if the soil needs to have what? Dumping of appropriate layers of elements like gravel, sand, so on. We might need additional soil coming out from other areas and delivered to the site. And for appropriate design. So we have to estimate soil for a good foundation that can carry the weight of a house must be well drained so that it is dry and not waterlogged. That's why sometimes we are using what? Gravel and sand. Because gravel and sand do not carry water, do not hold water. So they cannot clog the passage of water. It is good if the water could pass along without damage rather than water gain pressure due to what? Due to water clogging. And the higher the pressure of water, it will later on break the soil elements. And what will happen? It's not only flooding that is important, but the soil that connects us from building, which is the footings in the foundation, will be without much support, okay? Because of flooding and the flow of water. It will come along with the flow of water. So water-clogged soil can become liquefied in an earthquake. That is another concept. If there's an earthquake, there is always an hazard that could place the soil under the ground to be liquefied. It will become water-like. And if the soil is becoming water-like, like mud, it is water-like, it will flow. And if the soil under your building flows, your building will flow with it. Turn to a semi-liquid so that the structure sink into the ground. So that's very critical problem. 1, 2, 3, 4. So there are 4 concepts here. So look. So we have the first picture, a small residential house. Okay. During construction, starting of construction, initial construction. So we are using what? What type of foundation is this? Okay. And look at the type of soil. What type of soil is this? So in here, we are looking at the area, if this is now appropriate for building construction. So it is not. It is not a good example because of bad foundation. This house is being built in a swampy, waterlogged area. Waterclogged. This is misspelled. Spelling's wrong. No? Waterclogged area. Okay? So we have water clogging here. So meaning the soil is not prepared. We don't prepared it by putting on a layer of sand and gravel. Sand, gravel, alternate layers could help very simply declogging the waterways. Okay? So very important because if this, it will continue to substantially affect the strength of the soil that that will support. If the soil is not good enough to support the building, what will happen? It is really a bad foundation. As the foundations and the foundation trench was dug, it filled with water, so the builders dropped dry sand and cement into it, and then the first row of blocks were located on top of this mixture. We usually see this in real life. This is what we see, how laborers and carpenters do it. They do not know. They do not have an idea that they are doing badly in this regard. Okay? Why? Because they just copy their bad experience. That's why. Number of years of experience is not the question. The question is, how good is your experience? For example, you have 2 years of very good experience against 30 years of bad experience. I may pick the 2 years of good experience rather than 30 years of doing the wrong thing. Having 30 years of doing the wrong thing is not a good experience. Okay? So, it is not the longer you work on the field, it is not the longer you work on construction site, it is how effective your work in the construction site is. Okay? Still, the foundation will be permanently wet and inadequate to support and bear the external hazard. So that is the analysis, no? That is the analysis. Another one, so we have some residential houses here near swamp or river. So I think this is flowing river. So we have what? Sandy and stony type of soil here. So this is again an example of bad location. This house is located on a river bed, close to running water. So this is the river, which is some meters away from your house. However, this is, for example, a natural or normal level of water. How about during typhoon? What is the level of water during typhoon? So the level of water during typhoon will go up to that house, up to the, for example, middle of the house. You will notice. You will notice the discoloration here of the cement. So maybe that is the indication of water level. So not only the house, but also its contents are vulnerable to destruction. Contents meaning those appliances, those properties inside the house. Because we are having house in order to store important and valuable assets. Okay? Whatever it is. For example, agricultural produce of how many kabans of rice. Okay? For example, 50 kabans of rice is a pricey thing to be damaged, okay, by a single flooding. So, it's a painful loss to the owners if that so happens. Houses should not be built in such obviously vulnerable location. However, we are always building those type of houses and in those types of location. They should be designed to resist hazard in their location. So, on the very first place, we are building our house in that hazardous location. Okay? We could build a house, some areas in the upper portion of the land. Okay? Within reach of the water level, that is hazardous. So, outside the reach of water level, the maximum water level. So, if you have what? You have one whole year of experience, 10 whole year of experience within that area, you will have what? An appropriate knowledge of what is the water level during the dangerous times. Okay? And that water level should be your basis in order to select location of your house. Okay? That's another thing. Another bad. The previous one is for foundation, which can be corrected. This one could also be corrected by dumping sufficient amount of soil before building a house on top of it. Houses should not be built in such obvious vulnerable location. Okay? And the next one, we have this example, or in a two-story house or building is what? Affected. This is uneven or unbalanced settlement. Okay? So, balanced settlement. That is an obvious result. Oh, how can you now correct this? More or less, you cannot repair this. You cannot repair this. You cannot repair this anymore. And how much is the loss? All of the materials lost. How can you repair this? It could be. It is still possible, engineering, but the solution might be expensive enough that you would even decide to build a new one. Okay? Liquefaction under the ground, meaning sudden exposure of the underground soil into hazardous earthquake effect. So foundation suffered from liquefaction, and therefore the ground will what? Be affected, not in symmetrical to your building, but unbalanced, and would subside unevenly to the ground. So that's why, for example, only one column was affected by the liquefaction, then it will tilt. Okay, so that's why we have a bad example of number one, which is the foundation. Bad selection of foundation. Design principles. Number 2. This is now for the structure. We are now talking of the structure. Number 2. So, I repeat, we are tackling 3: foundation, structure, and the drainage. Okay. So, number 2 is coherent structure must be there. Regular structure, integrated structural ring beams around tops of doors and windows connected to columns. So, there must be transfer of loading around and among your structural elements. Proper transfer of loads. So, an integrated structural ring beam around top of walls connected to columns. Okay? So, beforehand, we have doors, windows, now walls. No? Triangular gable and walls must be structurally supported. Okay. So, let us take a look on examples. Okay. So, we are now looking not on the foundation but on the structure itself. Okay. So, what is this? We have a 2-story residential building, and observe properly the structure. How about the walls? How about the windows? How about the doors? And how about the columns here? Okay, columns. Okay, what can you say about those connections? Okay. So, this example is regular structured building. This is able to withstand the impact of hazard. Notice the structure of columns and floors, which are all joined to each other in regular format. Overhanging parts of the building are all well supported by continuous columns to the foundation. What are those? This one. This one. Okay. Overhang, but with support of columns, proper support of columns. Okay. So, we are avoiding the cantilevered type of application. We are supporting it simply or in continuous way, continuous support. Okay. So, take note, columns and beams and doors, windows. So, they are fixed with each other. So, the distribution of loads is proper and regular. Another example we have here, skeleton, structural skeleton of a building. So, 1-story building. Okay, take note. So, we have what? What? Okay, support for walls, supporting the doors above and under. Okay. So, we don't have windows. Do you have windows? So, the walls are supported by this structure, okay? Going to the columns, and also the trusses supported by beams. Okay. And, okay. So, let us take a look. Because of this is also a good structural design. Okay, take note, hollow blocks or brick wall with reinforced concrete structure. So those protruding parts are the reinforcement. So what we call reinforcement. A complete structural frame around the building is tied into the foundation. So you will notice that. Tied to the foundation. We have the foundation here. This is what we call tie beam. This tie beam, this is also form of foundation. Okay, because it is now connected to the footings below the surface of the ground. Okay, so these are the reinforcement. Okay, and the connection, complete, full connection. So good structural design. The top of the walls is also tied together with the columns. Okay, and by a second reinforced concrete ring beam. Okay, so what is this? Second, ito. This is the second reinforced concrete ring beam. This one. This is the first, the second, before we managed to go into the roofings. So there is what? This would support the doors and the windows also. And you'll notice those are connected to all of the columns. So very good. Very good. What? Transfer of load should happen in this type of design. And end walls are strengthened. Strengthened. And end walls. Okay? End walls strengthened. So there's no what? End walls. End walls strengthened. Here. There's no what? For example, here. This will become what? This will become windows. So strengthened, meaning hollow blocks is not exposed. Okay? Okay. Doors and windows have a beam over them to carry the weight of the wall above and to strengthen the columns. That is one way of doing it. Sometimes in the Philippines, we do not utilize this. We do not have this because beams, columns are very expensive. That's why, if you can recall previous slide, we have what? Foundation, which immediately proceed with what? Hollow blocks. So we are better if we use this tie beam. And also, above the doors, we have another beam. Okay? That would support this portion, this space. This space will be supported by that. In the Philippines, what will happen is that there is no such type of beam in the Philippines. Almost always, 90% of the time, particularly in residential area, even in this building, you will not see a beam above the doors or the windows. Okay? Okay? So, we will just what? Using lintel. We are just using lintel in the Philippines. Okay? A complete structural frame around the building is tied to the foundation, the walls, and the roof structure. So, very good. Very good. Let's go to the next. We have here a brick wall system, but notice the skeletal structure. Notice the skeletal structure. Okay. So, this may form a ring beam, but look at this. This is not a ring beam because of zigzagging, no? There are zigzagging. However, they are connected to the column. What will happen? So let us take note. Let us evaluate. It's still a good structure because it utilizes a good design principle. Notice the good foundation. Yes, we notice that here. This is part of the foundation. These tie beams are part of the foundation. Okay? The good structure framing the building and the two ring beams connecting all the building elements at the top of doors and windows and at the top of the walls. Okay? Two ring beams. So we have ring beams here at the top, but our ring beam here is also a ring beam. If you look from above, even though they are not what? They are not at the same height, it doesn't matter because they are tied at the column. Tied at the column, tied at the column, tied at the column, at different height, but also tied at the column. And also take note, they are not substantially apart from each other. They are near within each other. So it's still a good design. No? It is not as if they are 1 meter apart from each other. That is not good. No? However, this case, for example, here, this is 1 meter up to that point. This is 1 meter up to that point. That's why he made another beam in between. That's why there are what? 2 ring beams. There are 2 ring beams connecting all the building elements at the top of the doors and windows and at the top of the walls. Okay, top of the walls. Okay. So this one would support that one. Okay. Ayan. So if they fail, they will not fail in bunch and bunch of ways. They will be damaged one panel at a time. That's the difference. That's the difference. They fail, for example, during earthquake. For example, the damage will be only in this area, in this panel, or only in this panel, or in this panel. And the damage will not go farther on the neighboring panels because of the presence of structural elements, column beams in between. Okay? So that is one good design technique. Gable end walls are also strengthened with reinforced concrete. So reinforced concrete. So here we can see this is going to be gable, that is reinforced concrete, gable roof, that is a gable roof. So we have steel reinforcement like this. Okay. So we also notice that. So that is necessary. Okay. Next picture. We have a very basic bungalow type household. So this is not good. You'll notice there is no column here. There's no column. Or even column here nearby. There's no beam here. There's no beam. If this will be damaged by an earthquake, all of it will fall down. Okay? All of it will fall down at the same time. It will not be damaged like this one. This will be damaged one panel, one wall at a time. This one. However, this will be damaged completely. This will be completely shattered by a single because they are dependent on each other. If this part is damaged, all of the upper part will be damaged. If this part will be damaged, all of the upper part will be damaged. It is not the same. If we take a look at here, if this part is damaged, all of the upper part is not damaged because they are connected to the beam and column. Okay? Only that small part will be damaged. Okay? That is the difference. Okay? So take note of that. Bad structural practice. This house has no structural columns, just like we have noticed. No ring beams to hold the structure together. There are no columns at the corners or within the walls. We look at it, the same evaluation that we observed. There are no columns and there are no ring beams at the top of the doors or windows or at the top of the walls. This building will have little resistance to being destroyed by any impact from nature like an earthquake or even wind from the typhoon. Okay? Okay, let's proceed. Another bad. You have a column, somewhat. Have a column. This is not a column. This is not called a column. This is just what? Masonry. Reinforced masonry. This is not a column. Okay. Example of poor structuring of a house. The columns are very poor. Still a column, but very poor, with concrete poured in stages. Okay. Actually, they are not poured. Maybe they are just made up by what? throwing the mixture of sand, gravel, and cement. Okay. Okay. After the walls were built up, because this is common issue with carpenters and laborers, because we would like to what? To minimize the cost of building a form. A form. So you have to build a form, and then before you can pour mixture of concrete. Huh? Not just on the issue of money, but on the issue of complicated job must be done in forming complicated forms. You don't have to form a complicated forms like this one, because you just need what? One plate inside and one plate outside, then pour, because in between there are what? Amount of what? Hollow blocks. And look at the hollow blocks like this, okay? It's not properly made up wall. It's not properly made up wall. It's not fully covered the steel so that the reinforcing will rust. The columns are too small and the steel is too close together. Take note, the steel are too close together. It's not good practice. Okay? The steel should be farther away from the center of the column. That is a main principle. Okay? The concrete was not tamped to ensure good compaction. So tamping, after pouring in the mixture of concrete, while it is still wet, you have to tamp it by a small stick, long but small stick, you have to tamp it so that we can avoid bubbles. Okay? Bubbles. There are the trap bubbles, air bubbles that are trapped inside that created those bad column structure. Columns should not be made to fit within the thickness of the wall because there is not enough room to properly cover the column reinforcement with concrete. Okay. Columns should not be made to fit within the thickness of the wall. Okay. Okay. So, it is just what? Rushing of work. So maybe the foreman or the carpenter is not aware, or if he is aware, he still do it in order to avoid what? Long period of work. Okay? This kind of column does little to give a house structural strength. It would have been better to have a proper column at the end of the wall on the right. Okay? The end of the wall here, this one. You should have a column here rather than here. So it's not proper. It's not properly designed. Almost similar. Small column, maybe small column, but another one. The column here is not sufficient. It's not sufficient. Not sufficient. We need column here. Okay. Okay to have beam here, but there is no connection. This is just a lintel again. This is the practice in the Philippines. This is the practice, normal practice in the Philippines. This is not good structure. Another example of house which has too little structure to brace the wall against lateral forces. This is a common construction fault with hollow blocks. Columns are inadequate, too small and poorly constructed, and there should be a reinforced column between the door and the window. So here. So we might have here, some column here or here. Okay. Because if we do not have, they will fall at the same time. That's the reason. The window and the door have inadequate structural support. Yes. When the forces of nature strike this house, it will progressively deteriorate and be hard to repair. It is harder to repair. Okay, so we have another example here. Okay. We have columns here, columns here, and they are connected by a ring beam. So, however, so we have a beam trusses here. So, trusses here. So, okay. So, probably enough to hold certain degree of load. A good pattern of reinforced concrete columns and beams to strengthen all aspects of the building, including support to strengthen the triangular gable wall, end wall, so that it will not fall when the lateral force strikes the building. That is usually the weakest point. This is the weakest point usually. They will fall down. So structurally supported with beam here, with beam here. So if it is damaged, this panel will damage alone. This panel will be damaged alone. This panel will be damaged alone, and so on. Small pieces of panels will be damaged alone. And because of that, smaller and smaller pieces of panels are harder and harder to damage. Smaller sized area is harder to damage than the large size area. Okay? So, that's why it's good. All end walls of this nature need a reinforced column to strengthen them, or they are liable to fall when the building is subjected to a major lateral force. It is also as a reinforced concrete beam to tap to all walls. Okay, so that is good. Good. So we have what? Here, beam here. Actually, we have beam here. Okay. Complete. It is complete. Completely okay. Okay. A good structural practice. Connection of wood frame building to concrete frame or brick stub walls. So this type of connection. So on our timber design. So steel framing, steel bracket that could be used to support our columns and become a what? Footings, foundation. Okay. Okay, so that is what? Support our stub walls. Okay. It is essential that a wood frame structure mounted on a concrete frame brick stub wall must be fully anchored together. So, fully anchored naman yan. So have a full anchorage here. So, full anchorage here. So, letter Y and footings. Steel bracket. Okay? So, then, because this is a timber, so we are going to have a bolted timber system. Okay? The wood column must be bolted to the bracket as shown, and the bracket must be fully secured into the concrete as shown on the right. So, the bracket is made of crocodile metal, must be cast into the bearing structure to provide the structural connection for the whole wall through to the foundation. So this will support the wall, and meaning the wall will transfer the load to this column, and this column will transfer the load to the to the earth by this foundation. And this is obvious. This is obvious that this will happen. It's obvious, okay? So it is a good sample. Design principles, number 3. Joining walls to roof structure, join walls to each other. Column reinforcement should protrude from top of concrete columns and be bent around roof trusses for structural strength. So the reinforcement should be bent around. So, and be strengthened. Or roof trusses should be strapped with metal ties to the wall structure. It could be strapped or bent around. Okay? Strap. So strapping with the metal ties to the wall structure. Okay? Exposed metal, column should protrude from it. So that is for what? For stronger connection. For what? Complete transfer of load from trusses, roofings to the column. Exposed metal should be painted with rust-proof paint to prevent corrosion. So because of the bended exposed metal, you have to give some painting to avoid immediate corrosion. Okay, let us go to the picture example. So, strap. So this is what we call a strap. So these trusses are strapped. So this one member of truss is connected to the other member of truss. So they are what? Stable enough because they form what? They form the basic stable geometric configuration, which is triangle and strapped to the column. So, and this beam has a protrusion to be connected to the succeeding element. Also this one, okay? Illustration of binding roof trusses to building structure. Roof trusses should be constructed over columns, and for a concrete column, the reinforcement should protrude at the top and be bent over to join the roof structure with the walls. So, metal straps. Metal straps is the alternative way of doing it. Metal straps or plates can be used for this role, particularly where building structure is made of wood. So that's why they are looking like that, no? Made of wood. Another example, bended. The protrusion, reinforced protrusion are bended over. So with what? Bracket. Okay? With bracket here, in joining the trusses element. So good example, roofing sample. Reinforced bent over roof truss to tie house structure to the roof structure. This is an essential detail in areas subject to earthquake and to winds to keep the roof of the house when the natural hazard strikes the structure. Such exposed steel should be painted with rust-proof paint to minimize corrosion. That's why you are now looking at some of the rusting. So immediately paint it with enamel painting for initial paint protection. Another example we have here, steel trusses connected to concrete beams and columns. So what did they do? What did they do? They have protruding. I do not see the bended, but they have a good protruding reinforcement. Good roofing practice, steel roof trusses are connected to columns through welding. Welded. I did not see the welding. No? So welded connection of truss members to column reinforcing steel. And purlins are welded with ties to roof trusses. Okay. So welding by Welding Technology. So that's one. Welded. Okay. So those are This will hold the roof firmly on the house in storms or other hazards from nature. Next picture, we have a connection. So there is no bending. Why? Why there is no bending? So this is incorrect roofing practice. There is no bending of or protrusion of reinforcement between the roof and the building structure. The roof is resting on the top, so it could easily be flown away by strong winds, subject to moving with high winds and other forces of nature. So it's not a good principle. So another design principle, the third one, which is became number 4 here, tying walls to building structure walls, tied to columns, protect them from falling. Tie the walls to building structure. Okay? Walls tied to columns, protect them from falling. Okay? Walls must be tied so they do not move separately when the forces of nature impact them. Wall ties should be hooked into the wall structure. Hook. Hook looks like this. Okay? Hook. So we have like this, a small hook. Okay? There are small hook there. Okay? So good tying practice and illustration for a wood frame building where metal ties are used to tie wall materials to the main structure of the building. The steel wall ties are to be at maximum of 40 centimeter spacing. Maximum. So the distance of this one to this one, that is what he is talking about. Maximum of 40. So 40 centimeter. So 40 centimeter is about 1.5 feet. Less than 1.5 feet. Okay. Okay. So we have same. They are the same. They are the same. 40 centimeter. Reinforced where metal ties are used to tie the walls. Steel wall ties are to be maximum 40 centimeter, a minimum of 8 mm diameter. So the size is 8 mm. So, and bent at the end. They are for all openings in the walls. So 8 mm minimum. That is used in the Philippines. So this distance from this point to this point to this point, maximum 40 centimeters. And they are sized number 8 or 8 mm. 8 mm rather. Good example of wall ties. Yeah, wall ties. So these are the wall ties. So wall ties, okay. Cast into columns to connect the walls with the building structure. Ties are to be at maximum. Again, from bottom to top of the wall. However, this illustration, they lack hooks at the ends at this point in construction. So, there should be hook shape. Okay? Like this, small hook. Small hook shape. Okay? So, we do not see hook shape here. Okay, so also top or bottom. This 1, 2, 3, 4. Okay. We should also have above going down. Okay. So to top of the wall. From bottom to top of the wall. Okay, going up. Must be connected there. And okay, what happened here? Result of no ties. Okay, so the wall and column just separates. The beam and the wall just separate. Yeah, there is no connection between the wall and the beam. They just separate. Okay? The main parts of this building withstood the forces of nature striking it, but the one floor extension collapsed. Okay? So extension, wall extension collapsed. Okay? The columns could not help resist the force of nature on the walls for this house extension because of the lack of ties between the walls and columns. The one floor part also lacked the strong structure. So it's not a good practice. You can see there is no reinforcement in between connecting the column to the wall. So we have the reinforcement shown here, but there is no connection from wall. So they just separate from each other. Result of lack of ties. Another example of what happens when the walls are not tied to the column. The wall panel on the left is moving away from the column because it has not been tied into the column. Moving away, the damage could be gradual. It's not an abrupt result of an immediate impact of typhoon or earthquake, but could be even naturally without experiencing typhoon, without experiencing earthquake. Naturally, it will what? It will little by little part ways with each other. Okay. Design principle number 5. Roof truss ties also needed to enhance safety. Joints of wooden roof truss needed to be bolted together and tied with metal straps to provide flexibility but not collapse under the forces of nature. Metal roof trusses must be welded together, welded to purlins and welded to wall reinforcement for strength. Okay? So that is the difference between wooden and metal. Okay? Welding technology and bolts. Okay? So easier for welding, but the technology needs what? Equipment, welding equipment, and skill and power source. Okay. However, for wood, we just need to prepare bolt and holes, okay, and metal straps. Okay. So let us take a look. So wood, bolts, and metal straps like this, brackets. Okay, good. Straps tying together the different elements of the roof structure and at this joint in roofing so that they will be held together when affected by extreme forces of nature. It could be metal plate like this, triangular metal plate could be used like this. Also, triangular metal plate could be like this. Okay. Okay. Also here, also triangular metal plate could be used like this. Also in here, also in here. So, another illustration of a good joining practice. Notice that for a wooden roof structure, wooden blocks should be used for support of purlins, not a single nail to the purlins into the truss. Okay. It's better to have that kind of support using wooden blocks rather than nailing. But, however, the natural and normal practice in the Philippines, again, is through nails. Okay? That is a carpenter and laborer type of experience. No? Strap, plate across, joint. Okay? Okay. So, there is no nails. Bolt lang siya, no? You have bolts, pins, or even, even nails that passing through this metal strap or plate. How about steel connection? So steel connection, welding are so much welding. Okay. Where roof is strongly connected to the reinforcing wall by welding. The purlins are welded to the roof trusses. So, what are the purlins? These are the purlins. These are the purlins that is welded here in this area. That is the welding of the purlins here. That is the welding. Okay? That is the purlins and welded to the roof trusses with the small brackets to make a strong roof structure. Small bracket, so U-type bracket like this, made up of reinforcing bars. Principle number 6, cross-bracing of walls and roof. So we need what? Cross-bracing to avoid being susceptible to lateral damage. No? In order to resist lateral forces, walls and roof structure need cross-bracing at all levels, particularly if it is a wooden structure. This is a major principle in construction of traditional houses. So if it is concrete, the concrete blocks itself forms the what? The bracing, the cross bracing. Okay. Okay. Example of cross bracing system for walls through walls and roof. No. Cross bracing 1. Okay. Another cross. This is a cross, full cross. So one diagonal, which is also called the cross. Okay. Okay, so here, another cross bracing, another cross bracing here, another cross bracing. Take note of the formation of the cross bracing. This one, this one, this one. Okay. So those are the types of cross bracing. Minimum, but effective. So for columns, walls, roof, under the house for a wooden structure, the cross-bracing system provides strength against lateral forces. This is a system used in traditional houses and needs to be continued in modern houses. What is this? So this is an old house, I think in northern part of the Philippines. Okay, so we have what? Very hard to believe that this will survive. Maybe it is a very thick wall. So if it is very thick wall, it may survive. But there is no bracing, so Batanes house. Traditional Batanes houses which have stood through many storms and earthquakes are well structured and supported with good corner columns. The corner columns is good. But these are stones, masonry. I think they have reinforcement here. They have reinforcement. But the corner columns are good. And also this one. Very good. Very good. And have good arcs. Arcs, that's what I've said, over doors and windows to bear weight down their sides. So there is no beam, but the arc provides the transfer of load from horizontal to vertical. That is the function of an arc. It provides the connection, the transfer of loading from horizontal to vertical. Okay? So that's why it is still a good. This is a good. Solid stone wall on a good foundation provides resistance. So that's why, because of foundation and structure, even the stone wall is enough, maybe. Okay? And it is not just maybe, because these houses already are tested for a long period of time. They are still there. They are still there through many typhoons. Okay? Okay, number 7. We are nearing the end of the document. Drainage principle. That is the last topic. Drainage plans are essential to good use. High rainfall area requires drainage plan for roof water to common drain. So there must be what? Proper assessment of how the water should flow and go for that plan. Okay? Levels of the drainage system need to be included in the plan so that rainwater flows away and does not form puddles. Does not have muddy puddles in the or within or near the foundation. Okay? That bred insects also another health hazard, biological, from houses, so sanitary in nature. That's why drainage is under the sanitary or plumbing. because plumbing is an essential part of structure. What are the very simple essential part? Structural, plumbing, electrical. So those three are the most essential part. With just those three, we can build a simple basic house. Okay? Drains should be covered or bridged where necessary to allow access over them for people and vehicles. So there should be a pathway for the people not to every day step on the drain system. Okay. Drains should have a V form at the bottom to reduce accumulation of water if levels are incorrect. Okay, V type of canal. Okay. Design principles: house elevation and location, safeguards house and contents from flooding, landslide, plus floods. Selection of location: the house floor should be elevated above the surrounding ground level, and extra height is needed in vulnerable situations such as location close to a floodable waterway or swampy area, or in a tsunami or wave-prone area near the sea. Extra height is best provided through stilts. So stilts. So bamboo stilts is okay. So we can see on the pictures. Houses must be located away from the places subject to landslide where soil may move down a steep slope. Debris flows where soil, gravel, and rocks may be washed rapidly down by the heavy rainfall and plus floods. Okay, let's take a look. Okay, swampy area. We need to have a first floor above the ground level. Okay? So that's why we have footings here, and they are what? They are constructing this floor beam. This is the floor beam. So the floor is going to be about 1 meter above the ground. Okay. House elevation. This house is being built in a low-lying area, vulnerable to flooding. That's why concrete stilts are being cast on pad footings to raise the floor level of the house so that it will not be flooded or subjected to dampness. Okay. So these are the stilt, concrete stilts. Okay. So concrete stilts. So casted on what? Footings. So we have a footings, pad type of footings, individual type. But we have what? Floor beam. We have floor beam. It's enough to support because there is only one, about or less than 1 meter. So that is enough. Okay? And we have build on a ridge, not a depression with trees to stabilize slope. Okay. So we have a slope here, but you have to build on a ridge, not on the depression. The depression must be here or here, but you are building in a ridge with your what? You provided this. You provided dumping of gravel and rocks. Okay. Build away from a stream, bed, or a gorge. Okay. So this is above the water level. So much above the water level. Water level is already under the ground, which you do not see. Okay, maybe here. If you have a nearby river or sea, you can actually observe the level of water. Okay, so that is a good way to estimate the water level. Build on a bank above a river valley. So this might be a river valley, but you are in a bank. So you have the bank here. You can build your house here. Not on the same soil type with the river. Okay? Build on higher ground near the sea. So somewhat higher, not on the level of the sea. So that's why I recommended from the body sample initially that we can still build a house near that river, but provide banking of the ground on building higher ground, or provide a man-made higher ground by dumping an amount of soil with substantial amount of rocks and gravel. Guidelines on where to build. This illustrates principles for locating houses in safer places so that house and contents will be less likely to suffer disaster. Okay? Another picture in landslide areas. So provide this in landslide areas. Proper distance, provide sufficient distance over non-compacted field soil, non-compacted field soil. So provide your concrete structure, okay? Extraordinary flood level, so in flood-prone areas due to rise in water level. So estimate that. That's what I'm talking about, the maximum one. Not the normal one. This is the normal one, but this is the maximum one. Over riverbeds or irrigation ditches, but you have to provide a strong column. Okay? Over sanitary waste, landfills, or construction clearings. Okay, you have to what? Do it with what? Deep type of foundation. Okay? Phreatic water table. Okay, so we have phreatic water table here. Steam rises, so it's not good. In volcanic areas due to sand balls and steam venting from the soil. So it's not a good, we are not to build. Sample of places where it is not dangerous, where it is dangerous to build and where houses may easily be destroyed. So that's why do not proceed like this. Okay. You are within the maximum. You are here. This may erode. This may erode. Okay. The soil is not stable. Soil is not, so here, you are not sufficiently at a proper distance away from the landslide area. Landslide area, and you still build your house here. So provide some separation. Also over non-compacted. Even if you have a support, this soil is going to influence your structure. Okay, so that is why those are construction principles and materials. So we are now on this part. Principle, building may incorporate all good design principle, and yet the way it is constructed may lead to its failure when the forces of nature are applied to it. This section explains good construction method and principle for choosing good materials for construction. What are those? Even with the best design for construction practices, wrong materials can prevent the house from protecting its resident. It is not constructed properly or wrong materials are used. The house may injure or kill people when outside forces impact it. In constructing a house, the first and foremost principle is to follow the design and not to cut corners by reducing design requirements. That is happening all the time. Okay, this is happening all the time. And the choice of building materials such as sand, gravel affect the strength of the building, and care must be taken to choose the best materials. Mixing good, clean ingredients with little water makes strong concrete. Wrong ingredients seriously weaken concrete. Strong columns provide strength to the structure. This form part of the principle which use the best in order to keep everything and everyone safe. Strong roof provides lasting weather protection. Tying walls to the structure strengthens the walls from collapse and in an emergency. Wells and septic tanks are essential health supporting components. So what are these? For plumbing system or sanitary of a house, and therefore must be planned wisely. Where do you put? You have to put those at a distance with this other source of water and your septic tank. Foundation, material principle must be founded on solid ground. Only broken rock should be used in foundation, not unbroken, rounded river stones. So they are what? Obviously, if they are broken, they are not slippery. They pose sufficient friction. Okay? Sufficient mortar is needed to join stones used in the foundation into one solid foundation that will not subside unequally. Okay? So by providing compacted amount of mortar, okay, in between stones. Okay? Reinforcement is needed to connect the bases of columns, reinforcing steel in the foundation. So there must be a connection from the foundation, the footings, to the column itself by using the reinforcing steel, and that is because of the need to transfer the load more efficiently from column to the ground. Okay, good material for foundation, broken rock. Okay, break the rocks rather than unbroken rocks. Okay, this material is of a harder rock or sufficiently large size so that rocks will not slip between each other. So sufficient what? Friction. If it is properly laid and properly cemented with column starter concreted into it, it will make a good foundation. So this is a good foundation. Okay? So poor material for foundation, round, river, or beach rocks. Okay? So does not pose so much friction with each other. Okay? Because they are liable to slip between each other. Okay? So they will settle unevenly. Okay? So let us go to the next foundation. Good concrete foundation. So concrete foundation. So that concrete foundation is below the hollow blocks. Below the hollow blocks. Okay? With what? Reinforcement. Okay? These houses have been constructed in dry trench. So there is no flooding. There is no clog water. Okay? So dry trench using good material, and first row of blocks was laid while the concrete was still wet. Starter bars to reinforce the hollow block walls are inserted while concrete is wet. So we have footings and wall hollow blocks. Okay. Construction and sand and gravel. Coral sand should never be used in any construction. Coarse sand should be sieved to remove stones, fine particles, and dust. Okay? So there must be range of, there is a design range of sand size. Okay? And if the sand comes from a dirty or seawater source, it must be washed. Washing of sand. Okay. This is one example of a bad concrete coral sand, using concrete coral sand. Okay? Example of disintegrating concrete flooring. Concrete is returning to powder. The only action possible is this point is to dig it out and to start again, wasting time, money, and resources. So there's no reinforcement even. Okay, so only loss of money. Good quality sand. Okay, this good quality sand is all of about the same coarse texture and does not have larger stones in or a lot of dust. Sand can be tested by lifting up a handful and letting it fall back to the ground. If a significant portion of it blows away instead of falling straight down, it has too much dust and needs to be sieved. Okay, that is how we do it in the construction area. Okay, in the construction site. Example of poorly graded sand. Mixture of small stone and sand. It's mixed with large stone so that it is already a sand-gravel mixture. If gravel is now added to this mixture, it will not be suitable for making concrete because there will be too little fine material in it to bind it together. So it will not properly provide the recipe, the proportion, because it mixed up already with the sand. Okay. Bad practice for materials. Debris should not be allowed to be mixed with any of the ingredients for making concrete. Such debris seriously weakens the strength of the concrete. this sand will need to be cleaned before it is used for mixing into concrete. So there are what? Waste, garbage with the sand. So plastic, leaves, grass, roots, shells, and other debris must be removed before using sand or gravel for making concrete. Harmful debris, particularly in terse concrete when it is mixed by hand on the ground. Gravel is best made up of crushed rock, not of river rounded stone. So crushed rock. Okay. So about maximum 20 mm is good. It's good. 20 mm is good. In order for it to fit within the and around the reinforcement and to strengthen concrete and have few smaller stones. It's a good choice of size. Up to 25 mm can be done, but a good one is 20. Mixing of concrete, good clean ingredients with limited water makes strong concrete. Ensure adequate cement is added, mix ingredients well, limit water, and use only clean water. Concrete should stand up when mixed, not flow away due to excessive water. Do not use any water that is salty. This destroys the concrete strength. Do not use seawater. Use only properly selected clean ingredients. Because of what? Because of the amount of salt that would prevent the proper bonding. Okay? This destroys concrete strength. Okay? Making columns. Strong columns provide strength to the building. All reinforced concrete columns should be made in one part before walls are built. They should not be made in small steps as walls are built. They should contain bars for wall ties and ring beams when constructed. Column reinforcement should be 4 vertical bars with hoops holding them together, spaced at approximately the same as the width of the column. Okay. Bars should be anchored in the foundation. Okay. Spaced at approximately same as the width of the column. So the smallest dimension of the column, so that is the what? The bars. End of the hoop still should be bent 135. So not just like this, but 135 like this. 135. So 135 like this. So like that. Okay. They should contain bars for wall ties and ring beams when constructed. Okay, so there must be a provision for the connection to the next element. For example, for ring beams and wall ties. So do not produce columns, small progression. If it is possible, do it in one pouring. Okay? Do it in one pouring so that one beautiful homogeneous structure will be built. Column steel must be covered with a minimum of 2 centimeters of concrete all around. So, what? Concrete cover. This is what we mean by concrete cover in our RCD subject. Okay? 2 centimeters. So, do not put pipes down the center of columns. 2 centimeters is 20 mm, so that is actually the size of your gravel. So that's why gravel could easily pass through. Do not put pipes down the center of the columns. Usually the case also, but there are designs that would use that. That is not actually generally bad. But the pipe that we are putting at the center is actually plastic pipe, which is not good. For what? For plumbing system, for electrical system. We are putting pipes at the center of the column. So that is not good practice, okay? So we have a good practice. We have a tie beam here before the flooring. So we have columns being constructed before walls on a base to raise the house above surrounding low-lying land. Reinforcement of columns continues from the footings to the floor. Okay? From the footings to the floor. That's one. Passing through the floors. Continues from the footings to the floor to provide structural strength. Okay? So, another bad example here of the column. Bad example, for concreting of corner column in a particularly important area. This is an important height. This is an important height. So, it will gradually rust and deteriorate even when covered with mortar. The column is not properly covered because the steel cage was wider than the width of the bricks making up the wall. The result is the formwork for the concrete was against the steel. And when concrete was poured, the steel was not within the column, but on its edge. The windows have been placed in the walls in a very weak way. All of this wall is weak and well subject to collapse under stress. Okay? So, the walls, this wall, in this window, weak connection. Okay? Okay. Okay, that is how, because the steel cage was wider than the width of the bricks. Okay, so because a very normal way happening in the Philippines, but that is a bad practice. End of steel bent at 135 degrees for earthquake resistance. So this is what we are telling you. So this bending looks like this. It's not 90 degrees, more than 90 degrees. This is 135 degrees, like this. This one. All of the ends, another end, that all of the ends are bended like that. Okay? So construction, reinforcement, strengthens concrete like bones in the body. Proper use of plain round bars is significantly weaker. So we have to use deformed and twisted deformed bars. So we have what? Here, plain bars. So deformed bars. There are plain bars. So, round bars, okay? So, structural deformed bars, okay. But round bars, it's not okay. They are mixed up because maybe the construction site is very far away from the hardware and they use the round bars just to proceed with the work. Without available stored material of deformed bars, they use the round bars instead. Roofing, a strong roof provides lasting weather protection. Roof trusses of wood should be made with triangular frame placed over columns and tied to them. Roofing supports for wooden trusses must be made of a block of wood rather than just a nail. Block of wood. Roofing structure should not be joined near the middle of a span and not joined with a 45-degree cut. Okay. Should not be joined near the middle of the span. Okay, so joining process, no? So here, with block of wood, not a good practice, near, but not over the column. Okay, it's not over the, this should be right at the column. Because it is going down, it will post load here. But this is very short. This is still okay, but they are not recommending it also I will not recommend it, but it is still okay. Very short distance away from the column. But it's not very good. It's not a good practice because this is continuous beam, and this continuous beam will what? Will bend in a terrible way. And it's not long enough, not bent over roof, so it's not bent over roof, so very small protrusion. So those are the mistakes. And to connect between roof structure and columns, this is a weak building method. So next, block. So this is good, using block and to support these purlins. Okay. Securing roof structure, do not use a single nail, which is a weak support and may corrode and cease its function quickly in the Philippines climate. Nails through the wood structure itself are also a weak support. You can nail it, but with support, better. Okay, very bad. Bad joining practice. So, very bad. 45 degree and the middle of the span. It will just connecting in the middle of the span at 45 degrees. Roof structure joint near mid-span with 45-degree joint. This is a very weak joint, not properly made, and it will gradually give way, leading to a sagging roof. It will not support workers building or working on the roof. Dangerous. Tying wall to the structure, how? Good connection. Wall ties to connect walls with the building structure are to be at regular intervals of 40 centimeters and extend from the bottom to the top of the wall. Wall ties must be cast into reinforced concrete columns along with reinforced ring beams. Must be cast into reinforced concrete columns along with reinforcement ring beams. Wall ties must be bent at the end of the hook into the wall material. Hollow block walls should be reinforced. Okay? Okay? Okay, so this is good. Good with the reinforcement connected there. Good example of how to insert wall ties into columns before they are constructed so that walls will be well tied in the structural columns. Okay, so again, reinforced hollow blocks. There is no column to wall connection. Hollow blocks have reinforcement, but I do not see column to wall connection. Maybe later, no? Through the height of the wall, reinforcing bar every 80 centimeter. 80 centimeter is the distance between this one to this one. So this one to this one, maybe 40, then 80, 80, 80, then 40, okay? Or less than, okay? This is concreted into the blocks throughout the height of the wall and is inserted into the floor or foundation when it is casted. It is a good practice to fill all holes in hollow blocks to provide further strengthening to the walls. Supposed to be like this, hook. I do not see any hook yet here at the top, at the end. You see, so must be hook. Wells, septic tanks, plumbing. These are the essential health supporting system to a house. A well should not be located closer than 30 meters. This is the code, standard practice. Meters to the nearest septic tank. Spear standard. Huh? If they are located closer, liquid from the septic tank may contaminate the well, which may bring disease to the users of that well. It is best to have a common water supply from a tested, clean source rather than individual wells. In urban areas, a common sewage system is recommended and not hard to install. Common sewage system. In rural areas, rainwater from the roof should be collected in covered tanks to provide a source of good household water. Bathrooms and toilets need to be well ventilated and to have a window. Okay. Collection, water collection facility. drums, collecting water from this gutter. So all of these roofing will flow water directly to the gutter, and the gutter is slanted with this small slope, 2%, 1% slope. 2% is good slope nearing this prepared tank. Good example, collecting roof water in tanks for household use. This water is freely available and is usually of good quality. If many leaves are not falling on the roof, it is good. And there are no pets like cats and chicken running around your roofings. A screen at the entrance to the tank will filter out unwanted debris. Code of minimum standards for house construction. So we are now talking about the standards. Last 2 pages. Foundation must be designed specifically for the house in its location according to the size of the house, number of floors, weight of construction materials. Okay? The foundation ground must be chosen. The height of the water table must be observed because we may elevate the flooring. The possibility of liquefaction of the soil itself. Each house must have a groundwater, household water, and roof water drainage plan. Foundations are to be made of crushed rock laid on solid ground, well cemented, with a slope of reinforced concrete laid on it, and has connections for the house structure cast into it. Brackets for wood structure, reinforcement, or concrete structure. Okay? Rounded river or sea stones are not to be used unbroken for foundation. So we must break the stones. House elevation, consideration. So this is foundation, house elevation. House floor must be elevated above surrounding area with special consideration for flooding, either by groundwater, CSO, or tsunami, storm, typhoon, and so on. Houses must be located away from places subject to landslide, where soil may move downward steep slope. Okay? Move it with certain distance away. And building materials, number 3, sand must be coarse, clean, and without stones. Should not contain dust. Must never be coral sand. If it is from seashore, it must be thoroughly washed first and contain no shell or coral fragments. Gravel must contain broken stones and not plain, rounded river stones. The maximum stone size for house construction must be about 2 centimeters. Water must be clean and free of salt and algae. This is for better bonding. Concrete, no vegetable matter is to be mixed into concrete, no grass, wood, leaves, or roots. It must be well mixed. Use a minimum amount of water. It must be steep. If the mixture flows like water, it has too much water, it must be vibrated or tamped with a round rod to ensure proper filling on the form and proper cover to all reinforcement. Okay? Tamping. Okay, so with the use of rod, round rod. Reinforcing steel, deformed steel or twisted deformed steel is best for structural use. Structural columns must be vertical and must be constructed before wall construction and made in one part. Must be made in one part, meaning the whole column is poured in one go. It's not by parts. One, then after 1 month, another, after 1 month. It's not good. Must be homogeneous. Okay? Structural columns, that's okay, must be integrally connected to the foundation. Integrally, meaning the concrete and the reinforcement must be in good connection. If made of reinforced concrete, must contain 4 bars. One at its corner of minimum size 12 mm and minimum spacing 12 centimeter. 12 centimeter minimum space. 12 centimeters. 12 centimeter. Okay. If more than, so you can have 6 or more. But minimum 4 bars. Okay. minimum of 12 mm. Okay? Vertical steel must have hoops around the outside of vertical steel must have hoops around the outside of a minimum size of 8. So, gano'n, ha? So, this is vertical steel like this, okay? 135 degrees. Column hub steel must be covered with a minimum of 2 centimeters of concrete all round. Hoops must be spaced at no further apart than the width of the column. To avoid a stone-rich mixture at the bottom of the column, the first mixture should contain a higher proportion of cement and sand and less stone because it will what? Subside at the bottom. So the first mixture. The second one is okay to go it further. Okay. Building structure. The building must have regular structure. Structure must be strongly connected from foundation through walls to the roof trusses. For reinforced concrete structure house, an integrated ring beam around the top of the doors and windows must be connected between and into the columns. So, ring, beam, top of the doors and windows. Second, the reinforced concrete beam must be connected and top of the walls with the columns. So, at the top, so at least 2 ring beams. Ends of the hoop steel must be bent 135 degrees as shown in the handbook. Triangular gable end walls of the houses must be structurally supported. For a wood structure, wood posts must either be connected directly to the foundation or if above stub walls must be securely bolted to the metal bracket connected into the stub walls. So metal bracket with the stub walls with brackets, okay, connection. Okay, so complete connection must be observed. Tying wall material to structural columns. Wall materials must be tied to the building structure with metal ties. Metal wall ties are to be hooked at the end. All wall openings are to be tied to wall materials. For reinforced concrete frame buildings with brick walls, ties are to be casted into columns at 40 centimeter spacing and are to be minimum of 8 mm diameter. Draining walls and roofs. In the reinforced concrete structure, column reinforcement should protrude sufficiently the top of the columns to be able to wrap around roof trusses and nailed with them. For wooden houses or in the absence of sufficient protruding steel strap should be sufficient. Okay? And then roofing and roof truss joints, all houses are to be completely framed, pitched triangular roof trusses. Roof trusses are to be placed over columns and tied to them as mentioned in section 7. Most roof truss joints, and particularly central ones, are to be bolted, not nailed, as explained in this handbook. Preferably bolted. Roof truss joint for 3 or more elements have 2 metal straps joined in each roof component. Wood blocks are to be used for fixing purlins to roof trusses. Joints in the roof structural woods are to be made with stiff joints, not with 45-degree cuts. Strapping of joints. The jointing connection is not 45 degrees. Joints in roof structure are not to be made near the middle of the span. Okay. Take note of that. If you have to connect one element to the other, do it in other areas, not at the middle of the span. Cross-bracing of walls and roof. All wooden parts of the house structure are to be cross-braced, stumps, walls, and roofs. Wood roof structures are to be cross-braced in both directions. So cross-braced. In this direction, like this. Drainage. A comprehensive drainage plan must be part of its house design, must include drainage grounds of water and household water, as well as of roof water. All drains must have a constant flow towards common drain. Drains must be covered above bridges for access across them where needed. The bottom of the drain should have a V formation to minimize water accumulation due to improper fall of debris in the drain. Well and septic tank. No well is to be constructed closer than 30 meters, the nearest septic tank. It is strongly recommended that the common water supply from the tested clean water source be provided for cluster of houses. For cluster of houses, and particularly in urban areas, a common sewage system should be provided. For rural areas, however, rainwater from the roof should be collected and can be used as needed. Okay? So those are, we will just send you the checklist. This is part of the appendix. It's not a part of discussion. These are to be listed, and for you to have a copy of this, we will send it to you. And how do we able to know if you want the copy of this listing? Please use the comment section or comment box below and tell us that you need this list of building component checklist. Okay? Okay? From here, this is again your Samurai Engineer at your service. Thank you for listening.